In this video, we'll be looking at Chapter 15, Section I.1 on the scalar product of two vectors. So let's consider two vectors A and B. So we have vector A and we have vector B and their components. And notice that I've drawn them so that these two vectors are emanating from the same point, meaning they're starting from the same point. And notice how they form an angle. We'll call the angle between these two vectors angle theta. Now your textbook has a very involved proof of what we're going to call the scalar product. And instead of going through it step by step, I'm just going to paste the proof here and walk you through it a little bit. So the basis of this proof is the cosine rule. And we have to go back to chapter 10 to remember what the cosine rule is. But essentially for any triangle, if I know two sides and the angle between, I can find the third side. And that's essentially what we're doing here. We're finding the third side. This is B minus A, or vector B minus vector A, or the magnitude of vector B minus vector A. And we're using the magnitudes of the other two vectors and the angle between them to calculate the length of this side of the triangle. That's the cosine rule. So let's go ahead and label this vector B minus vector A. And that vector would be pointing in the downward direction. So let's walk through the proof a little bit. Here we have the modulus of this vector, and remember the modulus is simply the magnitude of this vector squared, and we have the magnitude of vector A squared here, the magnitude of vector B squared here, and then 2 times the magnitude of vector A times the magnitude of vector B times the cosine of theta. However, vector B minus vector A is this in component form, and this is just a simple subtraction, right? We have the x component of B minus the x component of A, and we have the y component of B minus the y component of A. Now there's a step that your textbook skips, and that is finding the magnitude of vector B minus vector A. And remember, finding the magnitude, we take the square root of the x component squared, which in this case is B1 minus BA squared, plus the y component squared, which in this case is B2 minus A2 squared. Now, I don't really want to take the square root of that. That's pretty nasty. But fortunately, look at what we're doing here. On the left-hand side of the cosine rule, we're squaring the magnitude of vector B minus vector A. So I get to take this whole thing and square it, and the square and the square root negate each other, and I'm left with just B1 minus A1 squared plus B2 minus A2 squared. So if you're wondering where that came from, that's the explanation. Now on the right-hand side, these two terms right here are the magnitude of vector A squared. So following the same logic here, we're squaring a square root, but in this case just for vector A. Likewise for vector B, that's where these two terms come from. And then that last part I'm just going to leave as minus 2 times the magnitude of vector A times the magnitude of vector B times cosine theta. Okay, we do a little bit of simplification here on the left-hand side. We're actually not simplification, we're expanding. Alright, the right-hand side stays unchanged. You know, this is just FOIL over here on the left-hand side. Right, we're expanding out these binomials. And then we have this nice long complicated equation. And notice on the left-hand side we have A1 squared, and on the right hand we have A1 squared. Those two go away. We can cross out a bunch of things on both the left and right hand sides and simplify, and we boil this whole thing down to a nice expression, this nice ending expression right here, and this is what we call the scalar product, or sometimes the dot product. And I'll tell you why we call it the dot product, because we use this notation, vector A dot vector B. Now this dot right here is not a simple multiplication dot, it's a larger dot, and it's used exactly for this purpose. It's the dot product between two vectors, and we often call this the dot or scalar product. And we do that, we call it the scalar product because if you'll notice on the right hand side, right, we have a series of scalars, and if we knew A1, B1, A2, B2, this would boil down to one single scalar number. So we're multiplying two vectors which have both magnitude and direction, and we're getting a single scalar number. That's why we call it the scalar product. And both of these expressions, the left-hand side and the right-hand side, are equal, and either can be used for the dot product or the scalar product. And I'll show you why we want to use either of those cases in a few examples coming up. Let's take a look at a few more things concerning the dot product. Again, we have vector A in component form and vector B in component form, and we have the dot product in two valid expressions for the dot product. Now, first of all, this middle expression here is known as the algebraic form of the dot product, because if we know the components of vector A and the components of vector B, we can just simply use algebra to calculate the dot product. And this expression on the right is known as the geometric form, because we're dealing with an angle here. Now remember, what we're really looking at here are two vectors that are emanating from the same spot, and there's an angle that forms between them. If that angle equals 90 degrees, in other words, if these two vectors are perpendicular, notice that the expression on the right becomes 0, and that's because cosine of 90 degrees equals 0, which means that the expression on the right, the geometric form of the dot product, equals 0. So this gives us a quick test to see whether or not two vectors are perpendicular. We can use the dot product if the dot product A and B equals 0, then vector A is perpendicular to vector B. Remember the symbol for perpendicular. And the quick way to calculate that is to simply use the algebraic form. So another way of saying this is if A1 times B1 plus A2 times B2 equals 0, then I have two perpendicular vectors. So let's take a look at an example. We have two vectors, vector P in component form and vector Q in component form, and we're asked to find the dot product between these two vectors and the angle between these two vectors. So the dot product is relatively straightforward if we use the algebraic form, which in this case will be P1 times Q1 plus P2 times Q2. We can find the dot product. So we have 3 times 2 plus 1 times -1. So we have 6 minus 1 equals 5. So the dot product between these two vectors is 5. Now we can use the geometric form of the dot product to calculate the angle between these two vectors. Keep in mind, the geometric form equals the algebraic form, so I now know that this equals 5. And the next step is to calculate the magnitudes of these two vectors. And we learned that in a previous video. I'm just going to separate these two steps with a line here. So we have 5 equals the magnitude of vector p, which is simply the square root of 3 squared plus 1 squared, times the magnitude of vector q, which is 2 squared plus negative 1 squared, times cosine theta. So I have 5 equals the square root of 10 times the square root of 5 times cosine theta. This is equal to 5 times the square root of 50 cosine theta, which is equal to 5 times square root 2 cosine theta. So we see that 1, we divide both sides of the equation by 5, we get 1 equals the square root 2 of cosine theta, and therefore cosine theta equals 1 over the square root of 2. But remember, I'm not done. I've been asked to find theta, so I need to do inverse cosine here. Okay, inverse cosine of 1 over the square root of 2 equals 45 degrees, exactly 45 degrees. Okay, another example problem here. We're given vector A in component form and vector B in component form, and notice that the x component of vector B is a variable t, and we're asked to find t given that vector A and vector B are perpendicular. So we need to use a property of the product rule here. Remember that if the product rule equals 0, then these two vectors are perpendicular. And the easier form of the product rule to use is the algebraic form. So we have A1 times B1 plus A2 times B2 equals 0. And this expression has to be true if the two vectors are perpendicular. So we can go ahead and fill in what we know here. We know A1 is 2. We know B1 is t. We know that A2 is negative 5 and that B2 is negative 3. And that equals 0. So now it's just a very simple algebraic equation to solve for t. We have 2t plus 15 equals 0. So therefore t must be minus 15 over 2, which we can write as negative 7.5. In this example problem, we're asked to find the measure of angle ACB for the 3 points given. So the first thing that we should do is plot these points. And we can quickly see that this is going to be a really small angle because my two vectors, my vector CB and my vector CA, are pointed in a very similar direction here. So let's find the components for these two vectors. So we have vector CA, and we can come up with these components pretty easily from the graph, or we could do it algebraically. But notice that I'm going over 1, 2, 3, 4 in the x direction and down 1, 2, 3, 4, 5 in the y direction. So my components for vector CA are 4, negative 5. I can do a similar process to find vector CB in component form, and I'm going to go over 3 and down 4. Remember the negative when I'm going in the negative y direction. Now keep in mind we've been asked to find the angle ACB, so let's use both forms of the dot product here. We're going to use CA dot CB, which is equal to x component 1 times b component, the x component of the first vector, which is 4, times the x component of the second vector, which is 3, plus the y component of the first vector, which is negative 5, times the y component of the second vector, which is negative 4. And that's going to equal the magnitude of vector CA times the magnitude of vector CB times the cosine of the angle between them. Remember, the angle is this really small angle right here. So I've got the left-hand side of this equation pretty well set, and I can start filling in the right-hand side. So I'm going to have 12 plus 20, and now I need the magnitude of vector CA, which is the x component squared, 4 squared, plus the y component squared, and we take the square root of that. Do a similar thing for vector CB. That's a negative 4 squared, times the cosine of theta. Let's get a little more room here. And so we have 32 equals the square root of 41, 16 plus 25, times the square root of 25, right, 9 plus 16, times the cosine of theta. Well, the square root of 25 is 5. That's convenient. So we can simplify the expression like so. Get a little bit more room. And we have cosine theta, doing a little bit of algebra here, we have cosine theta equals 32 divided by 5 times the square root of 41. And in this case, I just need to take the inverse cosine of this. Remember to use degrees here. Of 32 over 5 times the square root of 41 equals theta, which is 1.79. So my drawing told me that I was going to have a very small angle, and the math shows me that I get a very small angle, so that makes sense. If I got something in the high 80s, I'd be a little worried here. But always use your common sense whenever possible to make sure that your answer is correct.